that's fine. Okay. Welcome everyone. So I hope you're enjoying the lunch, and we are very happy to have Noah Zilberman from the Gravity Initiative to give a talk today. So she's going to talk on the quantum effects inside black holes. Noah, please take it away.
Thank you very much. It's great to be here. I'm a new postdoc here at the PGI, and this talk is going to be based on my PhD with Professor Amos Ori. So the topic of this talk is quantum effects inside black holes. And I will stand in here. Okay. Okay, it doesn't work. Just a second. Okay. So the analytically extended Kerr and Weiser-Nordström metrics, which correspond to rotating or spherical symmetric black holes correspondingly, reveal a traversable passage through an inner horizon to another external universe. And this remains the case in the more physically realistic scenario of a gravitational collapse, where only the ingoing section of the inner horizon maintains the role of a Cauchy horizon, being the boundary of the domain of predictability for initial value problems formulated outside the black hole. And I will talk a bit more about that. That's just an opening story. Okay. Now, imagine a traveler intending to access this other external universe. So in order to do so, she must pass through the black hole interior, and in particular, through the Cauchy horizon. Now, what will she encounter along her way? Is her mission doomed to fail? And does this other external universe actually exist? So answering these questions requires one to understand the manner in which quantum effects change or modify black hole interiors, and in particular, at the Cauchy horizon of a black hole. And this requires the computation of the renormalized stress energy tensor on black hole backgrounds. Okay, so that was just an opening story, and we'll go back to the story at the end to see what happens to our traveler. So in this talk, we'll start with an introduction, motivation. It's supposed to be rather accessible. Then I will just give you a few preliminaries. Then we'll see what the naive stress energy tensor is. Then we'll renormalize it. And finally, we'll see some numerical results of our recent works in Kerr background, also in Weiser-Nordström. And we'll conclude with a very preliminary discussion of back reaction and a summary. Okay, so so we are going to enter a black hole. So I guess most of you, all of you know the Schwarzschild black hole. So the Schwarzschild black hole, this is the maximally extended spacetime. It has a singularity at the future of all time-like curves that, or null curves that enter the black hole through the event horizon. And now this brings us to the question, is reaching the singularity inevitable inside all black holes? And it turns out when you add angular momentum, it might change stuff, and also adding charge. And when we add angular momentum to the black hole, which brings us to a more physically realistic situation, we get the Kerr black hole, and this spacetime now opens up in both directions to an infinite succession of black holes and universes. And this is the maximally extended Kerr spacetime. It has an inner horizon and a singularity. And this remains the case even in gravitational collapse. So just a quick tour into a rotating black hole. Of course, an isolated rotating black hole. On the left-hand side is just space for those of you who are not used to space-time diagrams like the Penrose diagram. Okay, so we begin in our universe, and we enter the black hole through the event horizon. And now we are forced to move towards the inner horizon. So the inner horizon, so inside the black hole, we are forced to move from R+ to R-, but then at the inner horizon, it's like after a waterfall, we may bounce back. So that's the inner horizon, and beyond the inner horizon, there's a singularity, a time-like singularity. and this time-like singularity is a ring singularity. It is gravitationally repelling, so geodesics tend to not intersect it, and we may cross the ring singularity to another. Here, there's another asymptotically flat universe. We can go back. We can keep traveling to all these universes and black holes that extend to our future. Okay, this sounds like not so much like science, but rather like science fiction. And this is the question that we want to answer. And it turns out that the inner horizon plays a key role in answering this question. Is this real? Okay, so the inner horizon, I will just move this so you can see. How do I? Okay. So the inner horizon has the role of a Cauchy horizon. So what's a Cauchy horizon? So here I'm just showing you the horizon Nordstrom black hole, but it's also in a Kerr black hole with gravitational collapse. This is the star, the surface of the star. Okay, so if we, sorry, this doesn't work. Try again. Okay, so if we put initial data on some initial data surface outside the black hole, and we evolve it forward, we are supposed to be able to predict the future uniquely in this domain of dependence, which we may also call domain of predictability. But as you see, this domain of predictability does not cover the entire spacetime. And its boundary is here. Its boundary is called the Cauchy horizon, and that's the inner horizon. Okay, so that challenges the core expectation of predictability in physics. So this intriguing fact has brought Penrose to postulate a strong cosmic censorship, which is basically just a question of predictability, saying that we must retain predictability, so the maximal Cauchy evolution should be inextendable. Inside black holes, that means that the Cauchy horizon should actually not be extendable due to the form of some irregularity, and there is a mathematical formulation which I will not go into here. And Penrose gave a nice heuristic argument to that. So if we have Alice and Bob, and Alice happens to live an infinite amount of time, and Bob enters the black hole, and Alice sends Bob periodic signals according to her time, Bob will receive those signals with an infinite blue shift as he approaches the Cauchy horizon. So that's just a heuristic argument on this instability of the Cauchy horizon. And indeed, it was shown that when classical perturbations are introduced, we get a weak and null-weak singularity at the Cauchy horizon, which means that the metric is not continuous. It is continuous, but it's not differentiable. And in particular, it is not tidally destructive. So tidal forces do blow up, but their accumulative effect on a traveler remain finite. So this was done in the charged case by Hiscock, Poisson, and Israel, Ori, and others, and in spinning case by Ori and Fermos and Nook. Okay, and this is reflected in TVV. So TVV here, so V here is a regular crystal coordinate at the Cauchy horizon, which vanishes there. So it was shown for scalar, for electromagnetic perturbations, that TVV behaves this way. So it diverges like V to the -2 with some logarithmic softening at the Cauchy horizon where V vanishes. Okay, so this is how this weak singularity is reflected in TVV. And this is related to how perturbations decay outside the black hole and how they evolve inside the black hole. So this brings us to the question, what do quantum perturbations tell us about this Cauchy horizon singularity? Will they introduce a stronger singularity?
Pen was 0, is that does that lead to infinite tidal forces? To destructive tidal?
Right. So here n, so you're right, if n is 0 and it is not 0, if n is 0, then we get a strong singularity.
I see. So the softening is just just because N is.
Yes, absolutely. Yeah. So n is some number larger than 0, an integer, that depends on the spin of the field. And it creates this softening that saves us from the strong singularity. But just as a side note, this does go with the strong cosmic censorship. So this does save strong cosmic censorship in the mathematical formulation of it. But still, it's a weak singularity. It is not tidally destructive. And we are asking, will quantum perturbations introduce a stronger singularity? So why should we expect such a thing? Since we are interested in quantum matter fields propagating on a classical curved spacetime, a suitable framework is the semi-classical formulation of GR. So this is the Einstein equation, and now we take the right-hand side to be the renormalized stress energy tensor related to some evaluated in some quantum field, in some quantum state. So spacetime curvature induces non-trivial stress energy in the quantum fields, even in vacuum states, which in turn deforms the metric through an effect known as back reaction. But this effect, what you may ask, quantum effects are really small, so how could this be important? So it's true that these effects are locally very weak. So the local semi-classical back reaction effect is typically of the order of the Planck mass over the mass of the black hole squared, which is really, really small. For astrophysical black holes, it's around 10 to the minus 77 or less. So that is a local effect, but these effects may accumulate over extremely long timescales, which may lead to significant global impact. And a very famous example of this is Hawking radiation, in which back reaction effects accumulate along the event horizon and then lead to a drastic reduction in its area due to evaporation, which contradicts classical expectations. So we see that quantum effects may be very important, especially when considering black holes, and they can dramatically change our classical expectations. Okay, so back to our question. Sorry, I see that I did not charge my, I'm so sorry. Does anyone have, can I run to my, just to charge my computer for a second?
I can.
Or, okay, thanks a lot. I forgot to charge it, sorry. Okay, so will quantum perturbations introduce a stronger singularity at the Cauchy horizon? Okay, so there have been a collection of analytical hints so there's an anticipation that stress energy fluxes will likely diverge at the Cauchy horizon, but without actual computations, thanks a lot. Without actual computations, this remains just an expectation. So our goal has been to address this issue via concrete calculations. So we started in the spherical charged case, and then we moved on to the more physically realistic spinning case. Okay, so we take an iterative approach. Yes.
But in the classical limit at some divergence of this response.
Yes.
Right? So the expectation is going to be stronger, or?
Yes, the expectation is that it's going to be stronger because outside the black hole, we have something called the Price law, which says that classical perturbations decay. Quantum perturbations don't have that Price law. So we don't have, we expect to not have this logarithmic softening that leads us from a strong to a weak singularity. But it was just an expectation for some decades.
And those ends that appear there, are they related to quasi-normal modes of black hole?
Yes, it is related to the tails.
The power law.
To the power law tails. It's directly related to the power law tails, yes. Okay. So now I'm starting to talk about what we did. Okay, so we take an iterative approach to the semi-classical Einstein equation. So each iteration has 2 steps. The first step is to compute the stress energy tensor on the metric of the previous step. So we start with a fixed classical metric, and then we may look through the semi-classical Einstein equation at the back reaction. But already at this leading order of just computing the stress energy tensor on black hole backgrounds, there's been a major difficulty that has hindered any progress for a long time. And this is the main thing I'm going to show you is the computation of this renormalized stress energy tensor on 4-dimensional black hole backgrounds. This is what we did. Okay, so I will have to tell you what is the background we are taking and what is the field we are taking. So charge is a poor man's angular momentum. That's a nice quote, because both Weiser-Nordstrom and Kerr, like I showed you before, have a Cauchy horizon. So we started with the Weiser-Nordstrom case just to practice, and then we moved on to Kerr. So I will focus on Kerr. This is the Kerr metric. That's the Kerr maximally extended spacetime. It has an event horizon, an inner horizon, and we are interested in sub-extremal Kerr. So A over M in suitable units does not exceed 1. Okay, and just to introduce, so we are interested in this red frame, which includes the exterior universe and what we call the black hole interior between the event horizon and the inner horizon. And this is what we call the Cauchy horizon, only this section of the inner horizon, because we are motivated by the case of gravitational collapse in which this does not exist. And just some coordinates. So we introduced the U and V Eddington coordinates inside the black hole, which go from -infinity to infinity, and the Kruskal V and U. So V vanishes at the inner horizon and it regularizes the Cauchy horizon. Okay, so that's just some background on the Kerr metric, so you know what I'm talking about. Now for a field, we take a minimally coupled massless scalar field. Okay, we start classically and we take it to be a quantum field and it obeys this Klein-Gordon equation. This is the covariance of the Lambertian. And this Klein-Gordon equation may be written on a Kerr background in this way. On its own, it's not that interesting, but you may write it in a certain way. But what's interesting is that solutions to this equation are separable. They admit separable solutions, which have a temporal term, where T here is time translation frequency. There are the angular terms. Because we are not in spherical symmetry, this is not spherical harmonics, but spheroidal harmonics. So these spheroidal harmonics satisfy these equations. And we have the radial equation. So because of this division by the square root, the radial function obeys quite a simple radial equation. I'm not showing you V because it's long. It involves omega in a non-trivial way, which includes the spheroidal harmonics. But this is a Schrödinger-like equation. It may be solved numerically, and the potential behaves like a potential well inside and like a potential barrier outside. And you may note that it behaves like 3 different kinds of frequencies squared at each of the asymptotic domains. Okay, so that's the field decomposition in Kerr into these solutions. Okay, and now this field, we should assign a quantum state to it. So we want a vacuum state, but in curved spacetime, there is no uniquely defined vacuum, because this would require a choice of decomposition in terms of positive and negative frequencies, which are not well defined in curved spacetime. So we take our field to be in the Unruh state, which is physically motivated, and it corresponds to an evaporating black hole. Okay, so in order to define this Unruh state, we decompose the field in terms of Unruh modes. So this is just a standard decomposition. This lambda over here is up or in, and I will show you this just now. Throughout the talk, when I say summation over L and M, I mean, you know, an infinite summation on L and a finite summation on M for minus L to L. Okay, so we decompose the field in terms of Unruh modes. So these are the annihilation and creation operators of this decomposition. And the Unruh state is defined with respect to this decomposition. So it is the state that is annihilated by all these annihilation operators. And it is defined within this red frame. So what are the Unruh modes? I will define them through their boundary conditions. Just a reminder on the coordinates, it's going to be important. So the in-Unruh modes just come from past null infinity as e to the minus I omega v Eddington, and they scatter and they enter the black hole. And they are decomposable in the usual sense because v here is linear in t. Okay, so we have e to the minus I omega t. So it is decomposable in the usual Tucholsky sense. But the Unruh up modes, they come from this hypersurface, so the past horizon and the left horizon inside the black hole. They come with respect to the, with positive frequencies with respect to the Kruskal u coordinate, which is not linear in t. So that means it is not, so every frequency, every Kruskal frequency has all the frequencies with respect to t. So that means these modes are not decomposable in the usual Tucholsky sense, which means it is they need PDEs to be solved in order to compute them. And we don't want that. So these are non-separable. They're not useful for computational purposes. So we introduce a different set of modes, the Eddington modes. So these are just a mathematical tool, and these are separable in the usual Tucholsky sense. They do have this e to the minus omega t times this radial function that I showed you. We just need to solve a simple ODE for that, and the spheroidal harmonics. So these Unruh modes, we have the exterior modes. The in modes come from PNI, emerge from PNI, from past null infinity with respect to the V Eddington coordinate, which again is linear in T. And the up Unruh modes emerge from past null infinity, again with respect to the Eddington U. So they are separable, and we also have a set inside the black hole, and again with respect to Eddington coordinates. Okay, so these modes, I introduced them because they are useful numerically. We can compute them by solving the radial equation I showed you before. Okay, so now we are interested in the stress energy tensor in minimal couple for a scalar field in minimal coupling. So what does that look like? Well, that's a classical starting point of for a minimally coupled scalar field. Turns out that the trace reversed version is nicer because it's just the product of two field derivatives. And then for the naive quantum version, I will just put expectation value. So when I say bare, I mean prior to renormalization. Okay, so that's the naive stress energy tensor. Flux components. So we are interested in the flux components because they turn out to be crucial for back reaction at the Cauchy horizon vicinity. So these are TUU and TVV, where U and V are again the Eddington coordinates. So in the Unruh state, at the event horizon, we have a negative TVV, which corresponds to the Hawking evaporation. And we have TUU is 0, because the Unruh state is supposed to be regular on the event horizon. And if this were not 0, then transforming to the regular Unruh, a regular Kruskal coordinate, we would get something that diverges. We would get a diverging TUU in regular coordinates. So TUU in Eddington coordinates is 0 in the Unruh state at the event horizon, but the fluxes evolve because of the curvature of spacetime. And at the Cauchy horizon, both flux components are expected to exist. And there's also a nice conserved quantity that relates these two flux components. Their difference times an area term is a conserved quantity, and it coincides with Hawking radiation when taking it to infinity per unit solid angle in the direction of theta. Okay, why are we interested in these flux components? So I will give you something about TVV. For TUU, it's a bit more complicated. But for TVV, just like I said, the TUU needs to vanish on the event horizon so that we don't get a singularity here. because we transform to regular Kruskal coordinates. So similarly, if we had non-vanishing TVV at the Cauchy horizon, when transforming to the Kruskal coordinate, which vanishes at the Cauchy horizon, we would get something that diverges like v to the -2. That's the strong singularity. Okay, so it is an interesting question. Is TVV 0 or not? And that's just one of the questions that we are asking. Okay, so we want TUU and TVV at r equals r minus at the Cauchy horizon. We want the renormalized quantities, but we start with the bare prior to renormalization. So as I said, the trace reversed is easier. And that's nice that GUU and GVV vanish at the inner horizon. So we actually have this very simple expression for the bare TYY, where y is either U of V, Eddington U of V, at the inner horizon is just this product of two field derivatives. Okay, that's a nice expression. We want to write it in as a mode sum. And if we decompose the field in terms of the Unruh modes, we get this mode sum expression. That's very simple, but it doesn't get us anywhere because we don't know how to numerically handle these Unruh modes. But as I said, we do have, as a computational tool, we have the Eddington modes. So we can decompose each of these Unruh modes as a superposition of Eddington modes. We do it in a very long paper, and we reach a nice result. So what we have here, that's the same result. What we have here is the spheroidal eigenfunctions. A and B are the scattering coefficients inside the black hole for the radial solution. And rho is just the scattering coefficient of the up modes outside the black hole. So these scattering coefficients may be computed numerically. And then we have something that is easy to handle numerically. All the components here we can compute. But of course, this expression, although it contains all the required information about the mode contribution to the flux component, the sum, of course, diverges. So this brings us to renormalization. So already in flat spacetime, this would diverge because of QFT, the way it works. But in flat spacetime, we can do normal ordering, and that would be the solution. But in curved spacetime, we don't have normal ordering, so it's more complicated. So a standard way to perform renormalization is point splitting. So I will now give you a brief overview of the point splitting method and the pragmatic mode sum regularization that implements it and state subtraction. But how much time do I have? Oh, there is a clock.
Half an hour.
Okay, half an hour is good. Thank you. Okay, so these are methods that we have been using in our research to compute various quantities, and the state subtraction one is the one that we use in this particular work. But I just want to give you a short introduction to point splitting as well. So point splitting, I will just demonstrate it for the field square. It is generally a method for quantities that are quadratic in the field and its derivatives. So for the field square, the idea is quite simple. We separate it into a product in two different spacetime points. So that's called the two-point function. We subtract something called the counter term, which encapsulates the divergence. And importantly, it depends only on the geometry. So in our case, it would just be, it goes like 1 over s squared, where s is the invariant distance between the points. Importantly, it depends only on the geometry. It's locally constructed, and it does not depend on the quantum state. And then after we do the subtraction, we take the limits. So it sounds simple, but because we need to, because the cases in which this can be done analytically are very scarce, this needs to be computed numerically, and this is notoriously hard. So this has hindered progress for decades, in particular taking this limit numerically. So this brings us to the pragmatic mode sum regularization method, which facilitates a numerical implementation of point splitting. The idea is, if we have symmetry in the background, we can split the points in the direction of symmetry, and then we can treat the entire split thing analytically, and the numerical computation is done in coincidence. So this would allow to mode-wise renormalization in coincidence. So just as an example, in the t-splitting variant, which is good for t-independent metrics, we split the points in the t direction, and then we decompose both the mode contribution and the counter term. We decompose it according to this split, and then we can take, so now everything is done at coincidence. We take the coincidence limit, and then we can subtract the counter terms on a mode by mode basis, and then sum and integrate, and this should give us the result. Okay, so that's a nice method that we use. But in our case, at the Cauchy horizon of a Kerr spacetime, this does not work. So this brings us to another idea. So schematically, the renormalized stress energy tensor, we have a bare quantity, we subtract some counter term, a diverging quantity that does not depend on the quantum state. Okay, why is this important? Because now we can actually take two states and subtract them, and then we get rid of this term altogether. So this circumvents the need to know this purely geometric counter term. So the idea is, now if we have two states, and we know the renormalized quantity in the what we call the reference state, then taking this difference should yield something regular. And that way we can find our regular renormalized quantity. So that's a very useful idea. So we construct a new quantum state, which I will not go into the details, although I think it's pretty neat. But I will tell you that it is inspired. So just like I told you that TUU has to vanish at the event horizon in the Unruh state. So this state that we construct is inspired by that, such that TVV vanishes at the Cauchy horizon in this other state. And this is a state that is based on this, what we call the negative mass universe, which is beyond the ring singularity, and which is kind of speculative, but it works. Okay, so we want TVV at the inner horizon in the Unruh state. We can write it in the state subtraction, according to state subtraction. And now we found a state, we constructed a state in which this is 0. So this is really very useful because it just leaves us with the two bare mode contributions that need to be subtracted. And we don't need actually to do any renormalization. So this is the expression I showed you before for the bare TVV at the Cauchy horizon in the Unruh state. And we construct the same thing in the U underbar state, in our reference state. And everything here is stuff that we can compute. We have the spheroidal harmonics, A and B and rho, which are scattering coefficients, and all of these can be computed numerically. And of course, what I wrote there is just a formal subtraction, and it is done on a mode by mode basis. So we subtract these per omega LM, and then we sum and integrate over all modes. And that's it. That's the recipe. So does the recipe work? So an important test would be, is this difference indeed regular? Because each one of those on its own diverges. And we empirically do this computation, and we find not only convergence, but exponential convergence in both L and omega. So that is very useful numerically. So we don't need to compute many modes because of this exponential convergence. And once we compute TVV using this recipe, we can compute TUU because again, they are related by this conserved quantity that has this very simple mode sum expression, it only depends on the outside of the black hole. This has to do with the fact that this conserved quantity coincides with Hawking radiation. Okay, so we can compute TUU from TVV quite easily.
Sorry,
Yes.
one question.
Yes, please.
Does the final result depend on the what type of a scheme you choose for the realization? Or it's a specific scheme, or it's
Yeah, so there are ambiguities, and when you choose a scheme, it also includes a choice of the ambiguity. But because we are interested at the singular stuff, which happens at the Cauchy horizon, these ambiguities are regular, and they don't contribute to what we are interested in. We are interested in the singular behavior that the ambiguity cannot be part of. Yeah. But in state subtraction, also this is reflected in state subtraction, the fact that state subtraction does not have any renormalization scheme involved. We just get rid of the divergence, and indeed, yeah. So there are no ambiguities involved. Yeah. Thank you for the question. Okay, so now time for some results. So once we have computed TUU and TVV at the inner horizon of a Kerr black hole, okay, so we start at the pole. The pole is theta equals 0. We start there because it turns out that only m equals 0 modes contribute. So it's much easier. So we compute both fluxes, TVV and TUU, at the inner horizon in the Unruh state as a function of the spin of the black hole at the pole. And we find, first we find that for smaller A over M, which is closer to Schwarzschild, both fluxes are positive and increasingly positive. Then when we go closer to the extremal limit of 1, then this is a zoom into this region, then there is a change of sign. And then they become negative, which is interesting. And then they approach 0 in the extremal limits. Yes, please.
You discussed doing the computation by comparing two states. So in the other state, your reference state, you also compute it on this. I can understand that your sum is just the difference between these two, but you also need to compute separately.
Right. Yeah. So the other state, oops, sorry.
Maybe it's regular.
Yes. So we constructed it such that it is 0.
So.
Yeah. So we constructed the state exactly for this for that purpose. Yeah. It is 0 because we constructed it such that it is regular at the Cauchy horizon. In order to be regular there, it has to be 0. Okay. So this is results in the Unruh state at the pole. So this is quite interesting, but it actually reminds us of what we found in the spherical charged case, where we did not do state subtraction. We did theta splitting, variant of point splitting. But again, we got increasingly positive values. I don't show you everything. We got increasingly positive values close to Schwarzschild. This is the Q over M axis, and a change of sign and approaching 0 at extremality. So it is similar. Okay, but so I will just say a word. So we can expect that Kerr at the pole will behave similar to Weisel-Ostrom, because at the pole we don't feel the rotation. So it is not surprising that this is similar. But now we get off of the pole. So we choose a fixed A over M value, fixed spin value, and we compute it as a function of theta. And this is something we could not have expected. Well, it starts positive at the pole, this we know. We know from the previous graph, but then it crosses the 0 twice and peaks at the equatorial plane. This is what happens at this A over M value. And so it might be specific. So these features might be specific to this spin value. but it is interesting, this variation in sign. And also, why am I always talking about this sign? It turns out, as I will show you, that the sign is important for back reaction. Okay. Now the near, yes, sorry.
Why do point splitting not work in the case of product?
Yeah, so point splitting. So I introduced the pragmatic modes and renormalization method, which needs to have a symmetry. So first, in Reise-Nordstrom, we had theta splitting, which we did not have in Kerr because we don't have spherical symmetry. And now T splitting. So it turns out that you can't do point splitting along a direction which becomes null. And at the horizon, this becomes null, the T splitting X and X prime. And then it just doesn't work. And this is manifested in the counter terms. You see that they go like 1 over the distance to the horizon or something like that. So because the counter terms diverge already in the separate limit, you will need an infinite amount of modes, and that won't be applicable. But maybe I must say it more softly that we don't know how to do point splitting at the inner horizon. Maybe there are methods, maybe that, for example, in Kerr, maybe we can take a combination of T and phi coordinates, and then it might work. But still, state subtraction is so much better because of the exponential convergence. So in point splitting, we usually get tails in omega and in L that we need to take care of. And state subtraction needs much less modes because of this exponential convergence. Yeah. So that's why this is the method of choice. And also in Kerr, we have phi splitting, which is related to the azimuthal symmetry. And it was used outside Kerr by Levy and Ori and others. But even so, this the related vector becomes null at the pole. So at the pole, it is not applicable. And even approaching the pole, it becomes very, very hard numerically. So it's really just an empirical result that it's really hard. Okay, but we might try to use it. Okay, so in just a few slides, I will refer to this. Okay, and now I also showed you in the previous graph at the pole that the near extremal domain, the fluxes go to 0. And it turns out that this domain, this near extremal domain, is amenable to analysis, to an analytical treatment. So it turns out that we can actually find analytically at least these two. Okay, so what we see here, the horizontal axis is the log of epsilon, where epsilon is a small parameter related to the near extremal domain. So extremality is there. And here we see various quantities divided by their leading order power of epsilon on approaching the extremal limit. And they indeed go very nicely, they flatten out very nicely to these values, these coefficients, which in this case, for TVV and for the Hawking outflux, we found it analytically. We also did it in the spherical charged case, and we wrote a whole paper about that analysis, if anyone is interested. So the powers we find are the same in the spherical symmetry. And so the powers of the small parameter are the same in spherical symmetry and in Kerr at the pole. So this is just a fun analysis that you can do. Okay, so our state subtraction method is new, and it uses a non-standard reference state, as I kind of hinted. So it is crucial to test it against other methods. And a standard method would be point splitting, but as I said, it is at least challenging, if not impossible, to do it at the inner horizon. So what we can do is to compute it on approaching the inner horizon and then extrapolate to the inner horizon. So that's what we do here. So these are the dots are point splitting results on approaching the inner horizon. So that's log of delta r. Delta r is the distance to the horizon. So the horizon is to the far left. And we find that these point splitting results do agree when extrapolating to the inner horizon. They agree very nicely with the state subtraction results, which are these horizontal lines. So that is one check on our method. But this was done only for this spin value and for the pole. We also did it for another spin value, still at the pole. So we might want one day to also get off the pole and check this off the pole. But as I said, it's much more difficult because at the pole, only m equals 0 modes contribute, and off the pole, you get, it's much more difficult numerically. Okay, and this is just maybe an advertisement for an upcoming paper that we also computed using point splitting, using the t-splitting variant. We computed TUU and TVV between the horizons. So from the inner horizon to the event horizon. So these are the results at the inner horizon, which we also got through state subtraction. But it's also interesting to see how it behaves as a function of r between the horizons. And we see a change of sign again. And we see that TUU goes to 0 as expected at the event horizon. TVV is negative as expected at the event horizon. We also did that for another spin value. Okay. So these are the results. Now we have some time for the speculative part, which is back reaction. So once we have computed,
May I ask one question?
yes, please.
Is there some explanation for why those were constant? As opposed to some other function that required the I guess the same version of the question is why goes there one over capital D squared?
So why does TVV go to a constant?
Yes.
As opposed to,
Well, it could have been. I guess you could say the other coordinates of the capital B coordinates are regular. Let's say it could have been any power.
yeah,
If the dimensional,
Yeah.
I would have guessed
Yeah.
it's 1 over B to the 4th. Why is it 1 over B squared?
yeah. Well, I think the easiest answer would be that we don't know to anticipate it. Maybe you know, but
And again, this is coming from.
that's true.
I guess we could
Yeah. So
offer an explanation in terms of some symmetry.
oh, okay.
Symmetry.
Well, TVV and TUU, they also exist outside the black hole, and they are related to Hawking evaporation. We know something about that. So they could have been 0. They could have been at the Cauchy horizon. They could have been some constant, which is positive or negative. They could have behaved in some other way. And that's why in the introduction, I said that there have been expectations, but as long as nobody did the computations, it was still an open question. So it is something that really needs to be shown numerically.
But presumably, it is related to the fact that in multiplication, flux, that part of its is constant.
Yeah.
So it's really that.
Right, so maybe one can say in this case that time translation symmetry implies that not even you, time translation shows you.
Yeah, so as I said previously, Hawking radiation is related to the difference between the two fluxes, which is shown here in green. So the difference, there is a good reason to expect that it should be constant because it coincides with Hawking radiation. But I think I personally could not rule out that maybe TUU and TVV, each one of them will have some strange behavior that will cancel out in the difference. I don't know if I could rule that out, but But this is what we get. We get constant results. And by the way, indeed, in Schwarzschild, they are expected to diverge TVV and TUU at it's not the Cauchy horizon anymore, it's the singularity, it's R equals 0. So yeah. Okay, so some very preliminary implications to back reaction. So first, as we said, having a non-zero TVV at the Cauchy horizon implies a curvature singularity, this v to the minus 2, with v Kruskal being 0 at the Cauchy horizon. So this singularity is strong, but it is strong when considered on a fixed Kerr background. So in that sense, when we compare the classical and the quantum on a fixed Kerr background, we get that the quantum perturbations indeed induce a stronger singularity than classical ones. So quantum wins the classical on a fixed Kerr background. And this is also what we found in Weiser-Nordström, and our colleagues in Leipzig found that in Weiser-Nordström de Sitter and Kerr de Sitter. So that's kind of a general behavior. Now, in the spherical charged case, we did some analysis, and we saw that at the Cauchy horizon vicinity, the R coordinate, its derivative in the y direction, where y is either u or v, goes like minus the corresponding flux components at the Cauchy horizon. So that means that R comma v goes like minus TVV at the Cauchy horizon, and R comma u goes like minus TUU. Of course, in the Kerr background, both of these are 0, but here they are not 0. So that means that the sign of TVV will likely determine the nature of tidal deformation. So if we have an infalling observer, by this back on the envelope computation, this observer will go abrupt expansion, abrupt because of this factor, abrupt expansion if TVV is negative, or contraction if TVV is positive. So the sign is very important. And the sign of TUU, I will not go into this here, but it might determine the fate of the Cauchy horizon itself. Whether TUU is negative or positive might determine whether the Cauchy horizon becomes a space-like singularity or a null weak singularity. But this is still very speculative. Okay, so going back to the story that we began with. So we are also finishing with the same story. So we have here our traveler, and she approaches the Cauchy horizon in this Kerr background with gravitational collapse. And now, according to what we said before, we said that we have a strong singularity on a Kerr background, and indeed, she is doomed. That's the answer to our question, but not so fast. The singularity was shown to be strong on a Kerr background, on a fixed Kerr background. So that is quite superficial because we don't have a fixed Kerr background because the background is evaporating. We are in the Unruh state. The background is evaporating. And this is already present at the event horizon. These back reaction effects related to evaporation accumulate on the event horizon. So this needs to be taken into account when evolving the Einstein equations from the event horizon to the Cauchy horizon. So just to give this, to illustrate this in the Weiser-Nordström case, so we can say that in an evaporating case, we can talk about back reaction in 2 stages. First, there is the soft stage, which is related to evaporation, which is already present at the event horizon with these M and Q. So the charge and the mass of the black holes depend on V on the event horizon, and they change as the black hole evaporates. And this is a very slow change. And at every point in the bulk, we have a Weiser-Nordström metric, like a local patch of Weiser-Nordström relating to the local M and Q values. So this is straightforward to analyze. And then we have the hard stage, which is related to what happens at the Cauchy horizon and to the sharp distortion that our traveler experiences due to tidal effects at the Cauchy horizon. And now The thing is, as our observer approaches the Cauchy horizon, she is exposed to different M and Q values and to different different fluxes that correspond to these M and Q values. And as she approaches really close to the Cauchy horizon, she is already exposed to fluxes that correspond to drastically different black hole parameters. So we cannot take an analysis of the Cauchy horizon on just the original background metric, but we need to take into account this evaporation stage. So there's a causal effect between the first and the second stages, which means that the actual characterization of the singularity at the Cauchy horizon, when we take back reaction into account, it may depend on the characteristics of evaporation, and it might be the case that it's even weaker than the classical. We cannot rule that out. So a quick summary. We used state subtraction and point splitting renormalization for novel computations on black hole interiors, in particular TVV and TUU, for scalar quantum perturbations at the Cauchy horizon. We found that they are both finite and generically non-vanishing, which means that we have this behavior of TVV in the Kruskal coordinates at the Cauchy horizon vicinity. We saw that the sign depends on the black hole parameters, both on the spin or the charge and on the angle in the spinning case. And the sign is important for back reaction, expansion versus contraction. And both fluxes vanish at different rates as extremality, A goes to M, is approached. And this near extremal domain lends itself to analytical treatment. So that was a summary, but the take-home message would be that through concrete computations, we have shown firmer than ever that vacuum quantum effects indeed induce a curvature singularity at the Cauchy horizon, both in the spinning and spherical charged case. As I said, what exactly is the singularity in the back-reacted metric still needs to be studied. And this validates a decades-long expectation and provides new critical information also about the sign, which is crucial for back reaction for tidal information. And of course, this is just one step in a broader exploration. And I will end with some future directions. First, back reaction is the motivation for this work, and that would be the most important future direction to take. Is the Cauchy horizon traversable? What is the singularity that forms there in the evaporating case? Several other extensions. So we have this parameter space of spin and angle. In the state subtraction, using state subtraction, we just went over two one-dimensional lines in this two-dimensional parameter space at the pole, and at a certain spin value, we went off the pole. And we also used point splitting to go off the R equals R minus. But there is still this three-dimensional space that needs to be explored. And another thing that is much more physically realistic is going from the scalar field to the quantum electromagnetic field. And now a new PhD student of my former advisor, her name is Maria Alberti. She intends to tackle this problem. And there was a new paper by Tyler McMaken from the University of Colorado that actually explored this green domain, this A over M versus theta domain, and explored it much more thoroughly. So that's really nice new extensions to this research. Thank you very much.
Thank you, Noah. Are there any questions?
Yes.
Do all the endpoint functions of the stress energy flux? Well, you look at the one for in general, I expect kind of all of them to grow.
Yeah, I guess they are related. So we are looking. So the short answer would be yes, I think so.
So then, would it make sense to ascribe a classical method even to this?
No, and that's why we take an iterative approach. So each time we look at it at each iteration, we look at the metric that was considered in the previous iteration, taking back reaction into account. Yeah. So the semi-classical Einstein equation, generally, it has to be self-consistent, but we cannot, at least we cannot solve it in a self-consistent manner. Yes, Alex.
So I have a question about states of subtraction. So the state you take has managed everything on the best practice, right? But when we normalize one, what we move away from the difference. So is there a way of defining that method also to find the part dependence?
Yeah. Actually, yes. So this is also some recent developments. So this reference state that we constructed, as I said, we constructed such that it is regular at the Cauchy horizon, unlike the Unruh state, which means that it is more or less its value at the Cauchy horizon when we are very close to the Cauchy horizon. It doesn't, so it has a regular behavior at the Cauchy horizon. So we may still do state subtraction on approaching the Cauchy horizon, and we get this singular behavior of the Unruh state, plus something regular that comes from the reference state, which we should keep in mind. It exists, but it's not dominant. So yeah, we can actually use state subtraction because of its regularity at the Cauchy horizon to get off of the Cauchy horizon.
But let's say it's singular event.
Thank you.
Sorry, may I ask, what is exactly the counter term? It's the background term, or it's different from this background term, counter term?
The counter term. It's complicated. Yeah, the counter term. So it encapsulates the divergence. The width did it in 65 for phi squared. For the stress energy tensor, Christensen did it in 70 something. Yeah, so it's not straightforward, I would say.
Maybe there shouldn't be any wave function.
Anyone?
Maybe you don't have any wave function normalization for this just answer. And since you have a shift symmetric scalar, I wouldn't expect even mass function. So I would expect it to be just finite function because it's speak. That's one is confused by your answer, but you can't put them as complicated. But just a scheme is complicated.
A scheme, yes, that's what I meant.
Yes.
Yeah.
About that, so you talk about the reaction, but is it even a question within Einstein theory, or is an R cubed term? I mean, since you have a divergence just done, so it's better if you have some R cubed term to your option, then you are going to change your answer completely. So it even makes sense to ask this.
That's a very good question. Yeah, and that's why I said that when I talked about back reaction, I said it's very preliminary because we need to ask all these questions and see what brings us too much away from the semi-classical formulation and what can we say within. So that's why I focused on tidal deformation, because tidal deformation already happens even if the background is still very much Kerr background. We still have tidal deformation. So we have to be very careful when approaching the Cauchy horizon. Yeah.
We think about this state that is regular at the inner horizon. That state earlier, I mean, before the inner horizon doesn't have some other funny features, because I mean, I find it a little funny that we find the state in the future with the moving singularity. So probably are also modifying it in the past. And I guess the question is whether it's singular or specific in the past.
Yeah. So basically, this reference state is analogous to the Unruh state, being time reflected and translated to that. So I
see. So it's regular in the inner horizon, but the singular in the original.
Exactly.
Horizon.
It's like if I will go back to this picture, you understood? Okay. This picture really helps to understand it. So very briefly, this red frame is where we construct the Unruh state. I'm saying it like hand waving, but we take it here to the blue frame. And because here we also have an asymptotically flat universe like this one, although it's a strange one. It has closed time like loops and that stuff. And then we define here like an analogous Unruh state, and then we reflect it through this line. And then we get that the Cauchy horizon in this green frame is like the event horizon for Unruh. That's the idea. But I must say that now we have more reference states in mind, which are less strange than this one. This was just at an initial. So this is how we made the progress, but now we have other states in mind, and the group in Leipzig, Holland, and others, they did something similar in the de Sitter case, and they also have their state construction, which is much more mathematically sound. So there are many states you can construct that will have this property.
Okay, there are no more questions. Let's thank Noah again.
The last I think you cannot trust the second classical.
I want to stop this. Yeah, I just remembered I need to stop this and I need to stop the recording.
I don't know how to do that. Oh, here.
Okay.